Alright, this is the first lesson on the next topic, which is thermodynamics. We're going to look at energy and heat in this chapter, or I'm sorry, in this video lesson. This is one component of a big topic called thermodynamics. We're going to cover thermodynamics in two sections. In this section, we're going to look at mostly thermochemistry. So this is a lot of review from honors chemistry. We're going to look at calorimetry and Hess's law and stuff like that. So there's going to be a lot of repeat. But then there is some new stuff that we'll look at, of course. So, all right. So thermodynamics is looking at heat and how we can use heat to generate power. Very important topic for our civilization, because we basically thrive and live off of heat. So we heat our homes, we cook our food, we run our cars, we do a lot of stuff with this thing called heat. I'm not going to go into too much here. I'm just going to get right into the material. So thermochemistry is really looking at the relationship between chemical reactions and energy transformations. In this case, chemical reactions and heat. So like I said, we're going to be focusing on heat quite a bit in this unit. Okay. So from physics, you should remember that energy is essentially capacity to do work and produce heat. I'm not going to go into much on this. You should know kinetic energy and potential energy. But as I said before, we're gonna get rid of this idea of work and focus solely on heat. Okay. So let's get into the chemistry part after we go over the units. Haha, I forgot about that. Okay, so yeah, you should know units. You should be familiar with this. From honors chemistry, this is Joule, named after James Joule, the person that figured out that that heat is energy. They originally thought heat was a substance. They called it the caloric theory. They thought it was a caloric fluid. And they actually thought it was something that was like a liquid that would pour from one thing to another. And so we talk about heat flowing and moving because they thought of it as an actual substance. Well, James Joule found that that's not true, that there isn't an actual liquid form of it, but actually an energy form of it. But the word calorie, that's where it comes from the caloric theory, still is around. And you got to be careful on the AP test because they do jump back and forth between these units of joule and calorie. Real chemists are going to use joules. We don't really use too much. If you're going into biochemistry and biology, they tend to stay with the calorie. Like our food is produced, they put on the labels capital C calories, which are actually 1,000 little c calories. So that's kind of misleading on the label, but you know, what does it matter if we don't really understand the connection between the two? But you should know. The AP test tends to go with more of the kilocalorie than the capital C calorie. But you should be aware of the various units in energy, and you should be able to do the conversion. I doubt that they're going to ask you to convert between the two, but this number 4.184 is going to come up quite a bit, especially when we get into calorimetry. So, all right, let's move on. All right, so if we're going to talk about energy and energy transfers, that's the thing that's confusing about this topic, is where is the heat and where is the heat going is kind of the idea. So we're going to start with defining two things. One is known as our system, the other is known as the surroundings. Okay, so the universe is basically everything. But what we're going to do is we're going to focus solely on what's called the system. That's the part of the universe that we're looking at and experimenting with. The surroundings is pretty much the rest of the universe. So for us in chemistry, our chemical reactions, things like water being produced by hydrogen and oxygen, would be an example of a chemical system that we would be looking at. Okay, so we'd be looking at this system. We want to know as these reactants convert to products. So essentially our system in chemistry are the reactants and our products. That's really what our system is in chemistry. It's a little abstract. It's not like clear cut sometimes, but just keep that in mind that we're looking at reactants converting to products. So our system is something that's actually undergoing a change, and that's good because that's where the energy is going to come from. So reactions are going to give up energy or they're going to lose energy. So systems are going to lose heat or they're going to gain heat. I'll talk about that in a second. Now it's really important that we keep in mind the point of view. It's what POV stands for. We typically take the point of view of the system. So we are always going to put ourselves in the perspective of the system. And I'll show you in this next slide why that's important. So if we talk about systems, you should know that there's two terms, exo and endothermic processes. So if this is our system, let's say there's a chemical reaction inside of here that's taking place in this flask. Well, we would think of that chemical system as really the system that we're looking at, and everything else, the flask, everything else. Here they're saying the flask and the contents, you know, really it's more of the contents than it is the flask. Anyway, so let's say heat comes out of this. Well, that heat has got to go into the surroundings. right? It's got to go from the system to the surroundings. So that's what we would consider an exothermic process, because we're taking the perspective of the system, and our system is losing heat. Heat is coming out of our system. So if we are the system, we are losing heat. We would say that that was negative. From the perspective of the surroundings, we are absorbing heat. So if we were witnessing the same process, but we were now the surroundings, we would experience energy being added to us, and we would say that that is positive. So it's important that we know which way that we're talking. So if energy is going into the system from the surroundings, going into the system, we would say that that's endothermic. Energy is going into it. We would put that as a plus sign because according to the system, we're gaining that energy. Okay, for the first one, we would say that that was negative, that we would be losing energy because we're taking the perspective for both of those processes as the system. I know it's a little confusing, but you really have to make sure that if you know that the system is negative, the surroundings are positive. Now, we're going to look at what's called the first law of thermodynamics real soon. And what that means is that this box is the universe, right? This little box is the universe. So that heat has to go into the universe, the rest of the universe, that is the surroundings. So whatever the magnitude is of the system, the surroundings would be opposite that. So these two would always cancel out. So the energy of the universe is always going to stay constant. That's one of the very fundamental ideas of thermodynamics. And we're going to talk about 3 laws of thermodynamics by the time we're done here. Okay, so let's continue here. So systems, there's 3 basic varieties of systems that we can have: a closed system, an open system, and an isolated system. This is the one that you really want to worry about, is a closed system. What that means is that energy, remember our heat, is going to be transferred, but no matter will be transferred for us. And we do that a lot in chemistry. Think about it. If we have a reaction underwater, we would have the reaction taking place under the water. Heat may be generated as this process happens, okay, or heat might be added to the process as this happens, but the matter stays under the water. Now, if you get bubbles coming out and you get gases forming, well, now you're going to be doing work, and we're going to limit that. We're just going to focus solely on heat transfer. So we're going to say that matter is going to stay within the confines of our system, so only energy transfers. An open system would be more realistic in just about all circumstances because that would be matter and energy. So like the Earth would be considered an open system because you can transfer matter and energy between systems on the Earth. Isolated system, we're going to come back to that when we talk about calorimetry, because this one is not a real true thing. We can't really get a true isolated system because one of the two has to be transferred between the system and the surroundings. So this is going to be an idealized version of it, and that's going to be used in calorimetry a little bit later. Okay, so let's take a look at work and heat. Actually, let's not look at work. We're going to actually drop this part out. We're not going to be focusing on work in this class. We're going to focus solely on heat.